So what I want to do today is get started with Bessel differential equation. It's something that we came across when we solved Helmholtz equation in cylindrical coordinates. So we need to know how to solve that equation. So before that, what I want to do is, because the Bessel function is represented in terms of something called gamma function, the solution. So I want to first talk about that, because when you start evaluating what is J0, J0, you know why the Bessel function is written in terms of gamma function, and then we come to because that's solving second order differential equation which you learned a little bit. And maybe go over some of the properties today of Bessel function. And then maybe next time we'll maybe talk about generating function for Bessel function and also integral representation for the Bessel function. Okay, those are the things that we do. Gamma function is nothing but, it's a way to represent factorials, a generalized way of representing that includes not only integers but any real number, okay, with half factorial, 3 half factorials, I can calculate all that. So for that, we'll go through the gamma function. We'll show that gamma function is related to factorials. Okay, so let's. This is the definition of gamma function. It is given by the following integral. Nu can be real or integer. Okay, I mean, so in general, our goal is to, so I'm going to call nu is real at this point. So that's a definition. So first thing is what we do is just look at gamma of nu plus 1, which is 0 to infinity. Okay, I have to just treat of nu dt, right? Has to become nu plus 1. And you just integrate this by parts. Okay, so let's first integrate this. Take this nu out and make this that. So what is the first step? All I did is integrate by parts, right? And that's all I've done. Okay. This is the first term, right? It's a negative, and then it's mu t minus 1, and there are 2 negative signs which cancel out, became positive. Okay. So all I've done is integrated by parts, okay, these 2 terms. So what's the first term here? 0, right? I mean, because nu is greater than 0, so we can, upper limit, this is becoming 0, lower limit, t is 0. Okay, so this is important, that's why this is important. So what we have is gamma of nu plus 1 is nothing but nu times, what is that quantity? Gamma nu, right? So, yeah, so this is nothing but 0 to infinity. So this is nothing but gamma nu. Okay, so this is some kind of recursion relationship we have. in gammas. What is gamma of 1? I just have to put can I say gamma of 1 is 1? Right? You put 1. What is gamma of 2? Is gamma of 1. System 1. Right? What is gamma of 3? 2 plus 1, right? So it's 2 times gamma of 2, which is, I can write it as, that's 1, so I can write this as 2 factorial. Okay. So gamma of 4, just put a couple of them, then you will see what it is. 3 plus 1, so it is 3 gamma 3, which is nothing but 3 times 2, which is nothing but 3 factorial. Okay. So what can we say about gamma based on this? What can I say if mu was at n, right? Gamma of n plus 1, what can I say about that? Or gamma of mu plus 1, let us say plus 1 mu. So we have this property, and then we also have, so based on this, because we know what is gamma 1 based on this definition, and then we are applying the regression relationship. So what can we say about gamma of mu plus 1? We say gamma of 3 is 2 factorial, gamma of 4.
Mu factorial?
Mu factorial, right? This one. So we have these properties. So that's the definition of gamma function. We have this recursion relationship, gamma of n plus 1, which is nothing but n factorial. Okay. So we are going to explore all these things. So this is true whether mu is real or integer, right? I mean, because we have just done it very general. Regression relationship is true. So in order to exploit this, right, this property, here the starting point was gamma of 1 for integers, right? I mean, we have to calculate gamma of 1. Gamma 1 is 1. Okay. So in order to calculate real factorials, right, of half factorials or 1/3 factorials, the starting point is 1/2 factorial. We need to calculate what is gamma of half. Okay, I mean that's something we have to calculate. Just as gamma of 1 was the initiator for using the recursion relationship, I need to know that. Okay. So let's try to see what is gamma of half, because that's the definition of gamma function, regardless whether it's real or integer. This is the definition. So if I, just as we calculate gamma of 1, can we calculate gamma of half to calculate fractional factorials? So if I just did this, what do I get? Just apply first the definition. Exponential of we calculate this now. Just substitution, let's try. Let's see where we go. Let's put t equal to x squared, something like that. Then I have et is 2x dx. T equal minus half is then, so I can write this as 0 to infinity. Exponential of negative x squared tip of minus half, that's what we wrote, dt is 2x dx. Exponential of the t2 of minus half is x power minus 1, right? So I have 1 over x right there. I have that is that, and dt is 2x dx. Can I write this expression as now what is that? Can I write that in a different way? Exponential of minus x squared 0 to infinity, can I further manipulate it?
Two times minus infinity.
It's 2 times or half times? It's even function, yeah, so, yeah. Half of, right, you know that, yeah. So, is half of Alright, done that. Still, we don't know the answer, right? What is that integral, right? I mean, have you ever done this integral before? Or to solve that, there's a trick here. How to solve an integral of, this is what I want, right? I mean, I want to calculate this integral. You know how to calculate it.
Can we square both sides?
Yes, that's the trick. Square both sides. What's the next step?
R squared equals x squared plus y squared. Change the order.
So we just change this to plane polar coordinates, right? I mean, so we don't go from here to the plane polar coordinates, then it becomes very easy to calculate. So what we're going to do is x is plane polar coordinates, x is rho cosine phi, y is rho sine phi, right? So, and then, so when you go from that, what do you have? I have one more thing. So x squared plus y squared is rho squared, right? So I can write that. And so 0 to infinity on the rho. And then what do you have? This is, how do you convert that? Dx dy, how do you want to do that? If you want to go to rho d rho d phi, what do? It's a Jacobian and then d rho d phi, right? So, so there's a Jacobian d rho d phi, and the Jacobian is what in this case? I'm just going to write it like this, the usual notation, right? So it's a determinant of partial x with respect to rho, determinant of partial y with respect to rho, partial of x with respect to phi, partial of y with respect to phi, right? And that is partial x with rho is cosine phi, right? That is, other one is sine phi. So that's rho, right? I mean, if you calculate Jacobian, that's rho. Is this clear? All right. So I'm going to change this to rho. My Jacobian is rho. And so d, so the integral over phi, that can be pulled out because that's easy. So all I'm left with is 0 to infinity exponential minus v squared rho d rho. Now it's simple, I can get ice and then calculate this integral. So I can cancel that, which is nothing. This is an integral I can calculate just 1, 0 to infinity exponential of minus d dt is just exponential of minus d with an negative sign at 0 to infinity. You can calculate. So the integral I squared is nothing but pi. Is it clear? Right? This is just 1. So what I have is, we were trying to calculate what happened to my gamma of half, right? Gamma of half, right? This is what we are trying to do, right?
Yeah.
Okay, so I erased it, so sorry. So gamma of half is nothing but, we calculate that integral, so nothing but, oh, that's I squared, so I is, we need that integral, I is square root of pi. Okay. So gamma of half is nothing but square root of pi over, did I get it correctly? Square root of pi over 2? Oh, did I miss a square root of pi over 2? Is that why I did it?
Yeah, but,
This half is there, right? Is this correct? Just check. I miss a factor of 2 or something. That was there. There's a 2 factor here. What was that? Let me just, where's that 2 coming? That exponential of minus p was x squared, right? So there's a, yeah. So there's a 2 here. There's a 2 here, right? We forgot the 2 here. Yeah, because I think it's there. So there's a 2 here. So that is 1. So I don't have that 2. So it's square root of pi. Gamma of half is pi. I wanted the starting point to be correct. I missed this 2 actually. I mean, we're focusing on converting that, I missed the 2. So it's gamma of half is square root of pi. Okay. So that is just as gamma of 1 was 1. This is something you have to remember. Gamma of half is square root of pi. So once you know that, you can get everything else. All right, is this clear? I mean, I missed this 2, so you have to, so gamma of half is that. Basically, that's gamma of half is nothing but, this is the integral that we had to calculate. And this integral is nothing but square root of pi. Okay, I mean, but the proof of that, you have to go through this polar coordinates, right? Plane polar coordinates, otherwise you won't get that. Now, okay, what is all the significance of all these things is the following, right? I mean, that's what I want to do. All right. So gamma of 3 halves is nothing but what? Half gamma of half, right? Which is nothing but square root of pi over 2. But this is what? Gamma of 3 halves is nothing but gamma of half plus 1, right? So what is this quantity that gamma of 3 half is, what is the factorial that we're trying to calculate?
Again, what the factorial of 1/2?
1/2, yeah. So we are trying to get now, this is gamma of 1/2. Because of this property, gamma of nu plus 1 is nu half. So gamma of half plus 1 is nothing but nu factorial, so it's half factorial. So what we have gotten is the following: half factorial is nothing but square root of pi over 2. Is this clear? So in order to do that, you need to know this property, okay, as well as that property, okay, to calculate. Now you can calculate any, fractional factorials or even negative half factorials. Gamma of negative integer factor doesn't exist because of that property of, the definition of gamma function. But negative half factorial we can calculate, okay. If you want to calculate what is gamma of let's say I want to calculate negative 1/2 factorial. What is that? What did you do for that?
You take a gamma of 1/2,
Plus 1? Yeah, basically that is a gamma of negative half plus 1, right? Which is nothing but gamma of half, right? Which is what we have calculated. So it's square root of pi, okay? So negative 1/2 factorial is square root of pi. Okay, once we have this, we can calculate practically anything, okay? I mean, 3 half factorials, blah, 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 okay? Meaning anything you want to calculate, you can calculate. Because we need this in, because Bessel function will come not only here, spherical Bessel, everything you'll have. And you'll have, because of the spin, you'll have L plus S, and S will be always half. You'll always have to, in quantum mechanics, you'll always have to calculate such things, to calculate wave function properly. So you'll have half factorials and stuff like that. Okay. So you need to know this. So the whole purpose of this was to eventually to calculate this fractional factorials, because we know how to calculate integer factorials. And so the definition that we had of gamma nu, so these are the only three things you have to know. Gamma of nu plus 1 is that what we calculated, gamma nu we calculated. Okay. Gamma of nu 0 to t exponential of minus t of nu minus 1 dt. Okay, that's the definition of gamma function. So that you have to know, and the recursion relationship, and then gamma of nu plus 1 equal to factorial. These are three important things, and then you can rest, that's a simple integral, so whatever it is, you can go back and calculate. Alright? So I had to go through that detour a little bit because we will use it to solve the Bessel differential equation and Bessel functions of different orders. All right. So we encountered this when you solve Helmholtz equation in cylindrical coordinates. So it's a simple non-spherical Bessel differential, ordinary Bessel differential equation. X y prime plus x squared minus mu squared y equal to 0. Okay, that's the, and mu is greater than equal to 0. And we'll consider the case when you use integer and when it's real, okay, both cases. All right. So what kind of solution should I propose for this? The CD solution, what kind of, for B case? So what is it? P of x here is 1 over x. Q of x is x squared minus mu squared over x squared. So both of them blew up at x equal to 0. But since x times p of x at x equal to 0, did we call s of 0? No, also let me write on that. That is what? Is 1, right? And x squared q of x at x tending to 0 is negative mu squared. So they are finite quantities. So the solution, the starting point, you have to check this. First, even one of them blows up for x tending to 0, then SPX, this becomes infinity, right? And this also becomes infinity because of this 1 minus something infinity, so it's infinity. So both of them are blowing up, right? So then we have to do this next check. Are they finite? If they're finite, we can propose Fubini series. Otherwise, you cannot even propose Fubini series. Okay, so that is what it is. But if this is finite, both of them, you go with ordinary part series. Right? So you don't have to calculate initial root equations and stuff like that. So this is an important check. In order to do this check, you have to put it in the canonical form. So those are important steps. Don't take P of x is x, and then you're going to think, then it says I'm blowing up. So. All right, so we have s of 0, this is t of 0. I'm also going to write it because we need the initial equation. Okay. All right, so the solution for Fourier series, how do you propose the starting point then? Y of x is summation x to the power sigma. Independent variable is x. I was about to put z, but okay, that's n going from 0 to infinity. Okay, you know the procedure now. So in order to get the solution, we have to calculate what the initial roots are and what the coefficients are. Okay, what we get from the recursion relationship will be ratios, and somehow we have to calculate solution once we have all that. So what are the initial roots of this equation? If you don't remember the initial root, you have to go back to substitute all this back into this equation. Look for what? X equal to 0, n equal to 0, the lowest term of the expansion, okay? And x equal to 0, and that will be your initial root equation, because sometimes after some time you may not remember, maybe remember for next week for the test, after 1 year you may not remember it. But at least remember that's how we get the initial equation, okay? So what is it? I mean, if you remembered it. Was it sigma times sigma minus 1, right? Plus S0, the one with the, that sigma plus, and the one with T0 equal to 0, right? So that's sigma square minus sigma plus sigma, right? T0 is negative mu square equal to 0. So sigma is either plus minus mu. Right? So if mu were, real, and if, not just if they're half minus half, we still have problem, we may not get to independent solution. So what that Fuchs theorem says is that if the difference between the roots is not an integer, then you can get two independent solutions. Okay. So it depends, right? In this case, we may have integers and stuff like that, but let us first assume that we have new1 and new, they are, like it could be maybe, we have to look at that. At least one solution we'll get it. Okay? So we have to find out how we can get second solution and stuff like that. If it's 1/3 or something, we still can't find it. So okay, now we have this. So let's get what's the recursion relationship? Let's start substituting this. Let's write this, and then so initial roots are sigma is plus minus mu. So we'll always take the first, the larger root. Okay, that will be the sigma 2. You will take it as negative mu, which will be the smaller root. Okay, so you will always get solution for the bigger root definitely in it. So that is something also you have to keep track of. Let's now get the recursion relationship. So you look at one of the parts, x to the power of n, some term, right, to get the recursion. So we have x squared, y double prime, n plus sigma minus 1, a sub n. So I have x squared here, so I'm going to write this as x to the power of n plus sigma. Okay, so let me take care of that. N going from 0 to infinity, right? Plus x times y prime, which will be nothing but summation a sub n plus sigma, x to the power of n plus sigma is my second term. Here the two terms I want to separate it out so that I can have correct parts of x. X squared y would be color match, so let me just put that here. X squared y would be plus a sub n, x to the power of n plus sigma plus 2, and that's the term. And all others have the same power. I think minus mu squared, summation n going from 0 to infinity of y, which is x to the power of n plus sigma a sub n. All I've done is substitute for all of them from that expression. Okay.
What's that minus 2?
Yeah. Okay.
The n plus r.
Plus 2 is it? X square, yeah, x square y, right? Yeah, plus 2. Okay, now x to the power of sigma is common and doesn't depend on, so we can pull it out in some sense, right? So what we normally compare is the power of x to the power of n. You can compare x to the power of n plus sigma also, it doesn't matter, okay? It will give the same thing. So, let us try to do that, and what do you get? What's the recursion relationship? And I also want you to look at this equation and say something about coefficient a sub 1, okay? I mean, so if you compare the coefficient, you want to compare the coefficient h to the power of n, okay? So that will give you a recursion relationship, right? So this will become, n has to become n minus 2, right? I mean, so that you have n plus sigma, so all of them are same power. So here you have to put n as n minus 2. If you want, you can separate that out, because this is nothing the same as x power n times x power sigma, right? So those, if you want, you can factor it. Or you can look at, you're really looking at the coefficient of x power n plus sigma if you want, either way, they are the same. So if you did that, what we have is the following expression: an n plus sigma minus 1 plus n plus sigma, and then this term, I'm going to pick up this term, minus mu square, and this I'm going to take the other side, and we have to change it n to n minus 2 to look at the same power. So there will be a sub n minus 2. Is there anything else? That's it, yeah, with the negative sign. Right, because I took it to the other side. So this will be, this is what you will get when you want to and you can get your recursion relationship from here, and you will put sigma equal to 1 or sigma equal to nu also. So this is n plus sigma square, and we can cancel, this will get cancelled. So what you have is an, what we have, n plus sigma square, right? Square, whole square, right? Minus mu square is negative an minus 2. Or the recursion relationship would be an over an minus 2 is nothing but negative negative sign here. For sigma, so we are going to first do it for sigma equal to plus nu, right? So we'll have n plus 2 nu times n. That's what we will have. Okay, we will put that in a minute. So this is your recursion relationship. So we will go back here and we have to find out what the solutions are, right? So let me just put here, and I want you to tell me something. So my first solution will be, now we want to choose sigma 1 equal to nu, right? Means what we have to put that. So we'll have a0, x0. I'm not able to do at this point, but I want you to say something at this point also. So on and so forth, right? Now can we say anything about, because this recursion relationship, if I put n equal to 2, I get a2 or a0, right? I just want, then I know I can get these coefficients, a2 over a0 and all that. So all I get is ratios of the coefficients from the recursion relationship. But can I say, and we know in that expression a0 is not equal to 0, right? That was also one of the solutions for the Houdini series. But what about a1? Can I say something about a1? Because if it is 0, then I can, get rid of all the odd terms. So let's look at the term n equal to 1. Just, I want you to understand how, what some of these things. That's how we also get, this is a series, we put n equal to 0, sigma equal to 0, n equal to 0, x equal to 0, and look at for initial group. Okay. So similarly, we can sort of guess some of these things by looking at this equation. That's all we have. So if I look at n equal to 1 means I'm looking at the power of x power 1. Okay, that's what we're looking at. So what do we get? N equal to 1. I have sigma minus 1, right? I want to say something about the coefficient A1, and I'm looking at power x, then I have plus n equal to 1, sigma plus 1. Sorry, I made it 1. N equal to 1 is, sorry, let's write it out. Sigma is also equal to plus mu actually, but we'll come in a minute. N equal to 1 is sigma plus 1. Yeah, n equal to 1, so it is sigma times sigma plus 1. Okay, that's what it is, the first term. And this term is A1, sigma plus 1, okay? And then, I will not have, x of n term at all because this higher part, so all I have is minus mu square A1. These are the only terms which have power, this has to satisfy that equation, okay, x to the power 1 term, that n equal to 1, that power x to the power 1 we are looking at. For recursion, x to the power n term we are looking at. So what is this saying? This saying is A1 sigma plus 1 whole square minus mu square, right? If you're looking at this coefficient, this has to be 0. And since sigma is new, this cannot be 0. So the only way to satisfy is A1 has to be 0. So what's happening is, this whole thing we also have for this differential equation, A1 has to be 0. So if A1 is 0, then I don't have to worry about A3, A5 and everything because of the nature of the recursion relationship. So if A1 is 0, all odd terms are going to be 0. So all I have to calculate is then, what does this expression look like for that is new decimal function, right? X power 1 is 1 plus A2 over A0 x squared A4 over A0 x to the power 4. So I need to analyze what these things are. If nu was, nu sigma 1 minus sigma 2 is not integer, I can put this negative nu and calculate the other one and put sigma 2 equal to minus nu and get the recursion relationship. Okay, so you get y1 and y2 also automatically. All right, let's see. What is A2 over A0? I'm going to put n equal to 2. And I'm going to now start putting sigma 1 equal to mu. Okay, sigma equal to sigma, the first root, right? We can now start substituting that. So that is, it is n equal to 2. 2 plus 2 mu, right? Looks like that. And sigma, that will cancel, right? So this is simply 2. N equal to 2. It looks like this. Can I write this as 1 over 2 okay, no, there's a negative sign. I should not miss it. There's a negative sign. The first one is negative. Alright, so this one I'm going to write as 1 over 2 square nu factorial over nu plus 1 factorial. this is where the gamma function will come eventually. Okay, I'll put it right now and then we'll write it. Okay, so that is what is happening here. Let's get A4 or A2 and then let's start predicting the general. So I just want you to, it's not just calculating a few quarterly, you have to predict the general term of this series. Okay, that's why you can write in a compact notation or analyze that series to a function. Okay, that's what we normally have to do. What is A4 or A2? I put n equal to 2, right, in that expression. And then n equal to, 4, right, then I get that. So I will have -1, n plus 4, n is 4, plus 2 nu, right, times what do you get? N is 4, that's 4, okay? So I need A4 or A0, right, not this, right? That's what I need for the expression. So this negative sign and that negative sign cancel, it become plus. And can you already see this a little bit like what is this particular one is looking like is nu plus 2, right? Maybe 2 square, I don't know, we'll see how the series becomes. All right, so A4 or A0, then I have 2 square, 2 square, 2 to the power 4 is there. Let me just write this as, and negative signs will cancel, I can write it as 2 to the power 4, okay? And then I have a 2 factorial, okay? This 2 I can write as 2 factorial. And I do have a new factorial, okay? And then I have what? Nu plus 2 times nu plus 1 factorial, right? Can I write this as 1 over 2 or 4, 1 over 2 factorial, nu factorial, nu plus 2 factorial, alright? This is coming from A4 or A2. I need to multiply by, to get A4 or A0, I have to multiply by A2 or A0, right? So I get all these things. Whatever I had previously, the 2 square here, 2 square 2 to the power 4, and I had a 2 here, so I combined all of them, okay? So all I'm going is using these two to get that expression, clear? So I'm going to write one more term and then we'll predict the general term because that's, so similarly A6 or A0, so to do the same process, what you have to put is n equal to, what do you do? N equal to A6 or A4 you get, right? N equal to 6 you put, and you get A6 or A4, and A4 or A0 is already calculated, so you can calculate A6 or A0. So that is the following number, 1 over 2 to the power 6, 1 over 3 factorial, nu factorial, nu plus 3 factorial. So pattern is not emerging. So the whole idea is I want to write the general term here, right? What is I don't want to just stop here, right? But I know I have all these things. I have all these A2 or A4 and all that. Maybe I'll write one, but then I just, I want to predict also. I want to use that, x squared. I have nu factorial, nu plus 2 factorial, okay. I have a sorry, I have 2 squared, there's a 2 factorial also, right? Oh, so here, mu plus 1, you put 2 squared, okay, fine. I have 2 factorial here, right? And then x to the power 4 is there, and then I have 2 to the power 4 is also there, I think. Okay. All right. Now I want to write this whole thing in a compact notation. I want you to predict the general term of this. What's the general term of that? What do we see? A2, we have A2 or A0, A4, A0. Can you see some, are we seeing some pattern here? I'm going to remove that because we don't need to calculate already, so we know where it's coming from. So you can start seeing it. That's possible. And this we wrote it as, sorry, I should have written as minus negative 2 square u plus 1 was there, so u factorial over u plus 1 factorial. That's how we do that. First, it's an oscillating series, that we noticed, right? I mean, it's changing sign. A6 over A0 it's negative. 1 over 2 for 6, 1 over 3 factorial, 3 factorial, u plus 3 factorial. So I want you to predict this term, a general term of this series, so that I can write this as something summation p going from 0 to infinity. So then all I need is what? I mean, these coefficients are calculated. I've already what? X to the power 2p is there, right? P equal to 0 is 1, p equal to 1 will be x squared, right? And then I have what? 2 to the power 2p perhaps, right? P equal to 0 is fine, p equal to 1 we'll have 2 squared, so I'm going to write this with that so you can start seeing that pattern, okay? And I have sign is changing, right? Can I put minus 1 to the power p to take into account of that? That is there. Now I need to write those kind of terms. This one is developing, which is slightly different. Okay, I mean that's why here I couldn't have stopped here. I mean sometimes you have to go beyond 2 terms. So this is like what? P equal to 0. This is P equal to 1, P equal to 2, P equal to 3, right? Let's see, like this is P equal to 1. Can I write this term first? Let's write down. What is this term in this notation? The general term that we are trying to predict is A That's what we're trying to do. I'm going to just so that let me call this 1 factorial. Here. So
Would it be, new factorial over new plus p factorial,
this is, yeah, this is your new plus p factorial, and this will develop into a p factorial, okay? So, so I'm going to put that also. Okay, so, and then what else? Right, I think we got everything, right? I mean, so that will, so this, in a complex infinite series, you can, put it in this compact notation. All you have to do is always predict a general term in this series. Then you can, if you are not able to convert it to function, this is what you should do. Look at the general term of the series. How can I write an infinite series in a compact notation? Okay, so always an over a0. In this case, because it's happening this way, I'm writing it this way, right? 2p times 0. So there's another thing that we can do here. We know that a0 is not equal to 0. That's all. We can take any value for it, right? I mean, usually. But I want to write it symmetrically. This is what is called a Bessel function. So I want to get to that form, what is called a Bessel function. This is x that is there, right? So I'm going to write it like this. I also have 1 over p factorial. I can write this as x mu plus 2p, right? I'm going to pull this inside also. But in order to write it symmetrically, if I pull that, I want to, because 2 is a constant, mu is a constant, I want to multiply and divide by this constant 2 nu, okay? So I can write this as x over 2 to the power of mu plus 2p, okay? So I'm going to multiply and divide by this, that I can do. And this is a constant, so I can pull it outside, okay? So this is also constant, it doesn't depend on p, so I can pull this also outside, right? So what do I get? I get y1x is a0, 2 to the power of mu, pull that outside, and nu prime also, let's pull that outside, and then I'm going to write the summation as the following, minus 1 for p, okay, that has been, minus x to power x over 2, now I can write in a compact notation like a mu plus 2p, right, I can write it like that, divided by p factorial times mu plus p factorial. I can write it like this, right. This I pulled out. This also I pulled out because it doesn't depend on p. I can pull it out. And I have x over nu plus 2p because I just combined them. So I can write it in a nice form like this. Now, so we have a solution, but what we call as Bessel function is actually the quantity within the square brackets. Since it's a constant, I can always take a0 equal to 1 over 2. We have been taking this 1, but now I'll take this as 1 over 2 nu times nu factorial. Nobody is stopping that. So this will drop off, and the solution is, this is what is called a Bessel function. Okay, so choose a0 equal to 1 over 2 nu factorial then my solution is then simply this. What we call as JUX. Is nothing but this summation. So what we generally call Bessel function is really this quantity within this square parenthesis. So all the properties will depend on what this is, right? Now, y2x, if sigma 1 minus sigma 2 is not an integer, is simply j negative mu x, right? So all I have to do is put nu to minus nu, and that will be my second solution. So this quantity here, nu can be half or something, then this is this factorial has to be not, normally you don't write it like this because if you are 0, you don't know how to calculate it. So you have to write it in terms of gamma function. People don't write it like this. This quantity will be written as, or this perhaps will never, but it will be half, can be fractional, can become. So p is always an integer, so it's okay. That can be left the way it is. This quantity is written as normally gamma of mu plus p plus 1. Similarly, this will be written as gamma of negative p plus. That's the correct way to write it. Okay. So so let me write it down. So this is normally then written as in this form. Mu factorial is what? Mu plus 1, right? So you have to add one to that. Mu plus p plus 1. Right. So this is the definition from which you can calculate J0, J1, J2. You have to look at the series, and we will do some of them. It's an oscillating series. J0x looks almost like a cosine series. It's not quite. It starts with a 1 and then it will, and J1x looks like almost like a sine series. And others are a little bit more J half and all will calculate. But all of them will require us the knowledge of how to calculate the gamma function that we have already, all the properties that we have learned. Okay, so let me just see what. So this is the most general solution of for Bessel function will be combination of these two things, right? be the most linear combination of that, all that stuff. Here I want to mention something, you know, as usual, like if nu in the Bessel function was an integer, the recursion relationship will break down, and so you get one solution but not the resolution, right? So there what you do is the following. There's something that it is, oh, let me keep this because I want to talk about something. Yeah. Neumann function or Bessel function of second kind they define. Let me just talk about that briefly. Also called as Neumann function. Because if j nu and j minus nu x are solution, I can hook up another linear combination, and the it's some weight factor multiplying j nu x. Okay. Right, this is what is called as Bessel function second kind. Of course, when nu is exactly equal to integer, it blows up because this is 0 and that will also cancel. Because of the property, this is what I want to talk to you a little bit. If nu is equal to an integer, we have this property j of negative nx is nothing but minus 1 to of n j sub nx. Now I'm assuming it is an integer, right? I mean, so what they do is to propose the second solution. One solution comes from, from this Frobenius series. To get the second solution, they don't put exactly equal to nu, but they propose a solution like this when they change it to nu, under variable nu pi. Limit nu tending to nu. Okay, so, or you can think of L'Hopital rule that you have to, because it becomes 0 over 0, you differentiate both numerator and denominator. So you form a linear combination in the not exactly equal to nu, nu equal to nu, and propose a second solution of that form. All right, that is for if the Bessel function has nu is exactly equal to integer. These are the tricks that are used. I want to prove this to you because when I have this on the board, I want to talk to you about that first, because that is something we may use. All right. So what we are saying nu is an integer, right? So Jn of x is given by so nu is now an integer. And I want to calculate j of minus nx. So we know all I have to do is first change n to negative n, right? Okay, I can do that, right? All I've done is change n to minus n. But I have to prove this, right? What did I say about factorial? Negative integer factorial.
They're invalid?
Hmm?
They're invalid?
Yeah, invalid they infinity. So this series can start at what location? That's the first thing to realize to prove that, okay? I mean, negative integer, because now it is not negative of half factorial or something, n is an integer, okay? This property holds good only when it's an integer. So since negative integer, if p equal to 0, I cannot define, right? So this series should start at what? 0 factor, does it exist? 0 factor is 1. So I can start this series from p equal to n to infinity. Okay, that's what happened because there's no negative factorial. Okay, so this series really starts at p equal to n. So that's the first step. So it is embedded in the property of negative integer factorials. So once you have it, then I can start off do some manipulations, right? And so let me just define change of variables like n plus p is under thing p prime. Okay, when p equal to n, p prime is 0, right? So I can write j of minus nx can be written as summation p prime going from 0 to infinity. Minus 1 of p is then minus 1 of p prime times p prime plus n, right? I can separate that out. So p is nothing but n plus p prime. All right, I'm taking care of p prime. N minus n plus p prime is p prime. Okay, so that is 1 over p prime. And x over minus n, that is minus n plus p is p prime. Okay, let's let that. Okay, p is nothing but p prime plus n. Okay, so 2p is 2p prime. Plus 2n, so that is 2p prime plus n. Okay, so let me just cancel all that. So this one will become x over 2 n plus 2p prime. Which is nothing but what? The summation, doesn't matter p or p prime is now a dummy variable, right? So I can put minus 1 for n outside, summation of p prime going from 0 to infinity, negative 1 for p prime, okay, p prime, right, n plus p prime, x over 2, n plus 2 p prime, which is same as j of nx. This whole thing j of nx is the minus 1, right? Because it doesn't matter p or p prime, I can make it, right? So what we have is this. So what we proved is j sub minus nx is nothing but minus 1 of n, j sub nx. Because this quantity here is exactly equal to, this is what we have here, right? So that's nothing but j sub nx, but they call it p prime or p, doesn't matter. All we have exploited, this is the only thing we have exploited. You put here, you have the definition of Bessel function, you just change n to minus n, okay? And we know that negative, now n is an integer, negative integer factor, they don't exist. So the summation, almost all the p from 0, all the terms will 0 to where n will vanish, right? Will not contribute. It starts at p equal to n. That's all we have done. The rest is nothing but just we manipulated. We want again back to, in order to get back to j next, I want is to start to p equal to 1 p prime equal to 0, we change a variable, and then you immediately get that. Is it clear or not? Yeah. All right. So next time we'll do more properties of Bessel function, but it looks like a beastly thing, but actually it's an oscillating, because you know that in a cylindrical drum you have to have oscillation. So what we'll look at is what does J0x look like or J1x look like, right? I mean, this looks like an infinite series, but it does, and J half x and all have in fact even compact. notation and compact analytical form. So we'll start looking at all these properties a little bit of this, it looks nicely compared to Bessel function, Bessel function, and the Lejeune polynomial also initially was the infinite series, right? But then we started looking at P0, P1x, and we had other ways of looking at the Lejeune polynomial. So the Bessel function looks complicated, but actually, that's how it is. It's a series function. That's what you're getting. You're going to get a series solution. Sometimes you're lucky to find an analytical form. Otherwise, it is going to a series solution. All right. So I think we should stop here. And any questions at this point?
Will Bessel DE be on?
Yes.
Okay.
Because right now we have solved the rest of it is general. So whatever we have done is second order differential equation for being a series, right? All we have learned is how to look at this general term looks like. Write it in a compact notation rather than naming it like an infinite series. Want to write it and then that's all. That's the only new thing. And we've got this new property today with and we learned about gamma function because we cannot evaluate negative factorials, negative non-integer factorials. I need to know gamma function. Otherwise, I cannot calculate the Bessel function. So that's the reason I thought I went over gamma function. Okay. So all you have to know is gamma of mu plus 1 is mu factorial. So that they are connected, because they look completely different gamma function starting integer or something. But the reason for that is I get it in the definition of Bessel function. So all these things we write as gamma of mu plus p plus 1, and this is gamma negative mu plus p plus 1. All right, let's stop here.